Welcome to Almost Here, Round the Corner of Future Technology podcast with Richard Jacobs. Future technologies poised to transform our lives for better or worse are the focus of this podcast. Almost here means these technologies are now here and starting to be used, or just around the corner, from Bitcoin to artificial intelligence, 3D printing, blockchain, virtual reality, and more. This is Richard Jacobs with Future Tech Podcast, Round the Corner, Almost Here Technology. Today I have a guest, very distinguished, Ilyas Khan. He's the CEO and founder of Cambridge Quantum Computing. He's also the founding trustee of the Stephen Hawking Foundation and also founding chairman, non-executive of the Stan Hill Foundation. He probably has 100 more accolades that I can't even talk about, but how you doing, Ilyas?
Hey, thank you. Thank you very much. I'm doing very well. Thank you.
Yeah, would you mind giving listeners, a bit more of your background? Because, I always find the guests can obviously talk about their background better than I could.
Well, at the risk of boring your listeners, I think on this occasion you've actually summed it up, and I wish there were 100 more accolades. But I'm London-based, and the centre of gravity for what I do is up in Cambridge. And as you've rightly pointed out, I'm the chairman of the Stephen Hawking Foundation, and that is a not-for-profit. I spend a little bit of time and a great deal of pleasure in interacting with that foundation. But my day job and the primary focus of what I do is that I'm the founder and the chief executive of Cambridge Quantum Computing. I've done a fair bit of technology-related work in the past, of course, but right now I frankly don't have much time beyond the two that I've just mentioned.
Yeah, until we get to quantum time management, that won't be possible, I guess.
Well, I'm finding that my children have an amazing ability to superimpose time, but that task is yet to be perfected by me. But it's obviously your comment prompted me to say that I think that of all the things I've ever done, quantum computing, at least the label, is the one that seems to inspire the greatest amount of interest in anything I've ever done. And at my age, I've done a lot. But at the same time, the correlation between what people think a quantum computer is and what it might actually be is also the greatest variance. So that in itself is a challenge.
Yeah, it's a big buzzword. So that's my first question. In real layman's terms, what's the difference between a quantum computer and a regular computer that we use nowadays?
Well, ultimately, of course, there won't be a difference. And that's the thing that needs to be said. My view is, and this is a view now honed over a number of years of talking to people about a quantum computer, it like anything else, like medicine, like psychology, like literary criticism, like philosophy, a lot of buzzwords, and ultimately buzzwords are just a code that allow practitioners to communicate well between them. As far as computer science is concerned, once quantum computing is prevalent, the ways in which it will impact our lives might have great meaning, just as things have changed greatly between the times of our, shall we say, grandparents, parents, and ourselves. There'll be progress, but a quantum computer will simply be a different way of computing, and it still will be a computer. There still will be instructions, there still will be a machine language, and there still will be outputs that are measured in the way that we interact with them. Things will be added, subtracted, multiplied, and divided, and it will be done in a different mechanism. When you look under the hood, the way in which it will be done, of course, will be very different. And when we get to that level of differentiation, the best way of describing the difference is that a quantum computer is a device that uses the rules of quantum physics in order to perform calculations that are currently performed in a classical manner using gates. It's the equivalent of comparing an abacus, which I would say is the existing computer, with a existing computer today. The difference between a quantum computer and an existing computer will be the difference between an abacus and an Apple laptop. And Richard Feynman, just to finish on that, Richard Feynman should be credited with this tagline that I'm about to give. Unlike all taglines and bumper stickers, it's great, but comes with a health warning. A quantum computer is a computer that computes in the way that nature intended. So all around us, nature computes all the time, and that's how nature is to be seen. And Richard Feynman said a quantum computer will allow us to compute in the way that nature intended.
Yeah, that's interesting. I've never heard anyone talk about nature computing things. What does that mean? Like, what's an example of something that nature computes, and how?
Well, at the most fundamental level, all matter, whether it's on the world or in the solar system or in the universe, is made up of certain foundational elements, fundamental elements. And these elements at the subatomic level have been given labels, electrons, photons, for example. And when we talk about nature computing, what we're talking about is nature operating so that a given set of circumstances, a given system, then mutates or changes or morphs into another, and that is a computation. So, for example, again, at a very, very general level, we have a reasonably good understanding of the way in which different atoms interact with each other and become molecules. That is a computation. That is simply one set of circumstances, let's say measured by a set of atoms, and let's say for the sake of argument that these are hydrogen atoms, and when they're interacting with oxygen atoms, as we all know, they become H2O, water. That is a computation, and that's what Feynman was referring to when he talked about nature's computation.
Huh, interesting, okay. And you talked about the parallel nature of quantum computing versus, I guess, the linear or step-by-step nature, what we have. How parallel could quantum computing be if you compare it to our regular computing?
Well, again, and using the same analogy, which was the one I provided, we have today an extremely effective and efficient way in which we manage ultimately binary instruction sets. So the computers we have today could be described as elaborate Turing machines, and we give them instructions and we tell them to do A or B or C. In all cases, the way in which a classical computer manages its instructions is measured in a form that is linear. But in quantum computing, a quantum computer, because it uses ultimately the laws of quantum mechanics, is exponential. And so a, shall we say, a binary instruction could suddenly be benefited in the way that we measure speed with an exponential speed up. There are some tasks in which that becomes extremely powerful, and there are other tasks in which we don't know whether it will become powerful. And to give you an example, an existing machine, an existing computer, no matter how powerful, finds it very difficult to locate and calculate prime factors. So if I gave you a number, a very large number, and I asked you to find its prime factors, you would struggle even if you had a very, very powerful computer. But a quantum computer, we now know, would find that task very easy and might be able to solve that task in a matter of seconds or fractions of seconds, where a classical computer might take thousands of hours.
Wow. Is that just because it's doing many more operations in parallel, or is it because it's doing that and each operation happens faster than happens currently?
I would. The problem with this, with labeling things like this, is obviously that we do fall into the trap of oversimplification. So I would say neither of the two. I would say that the better way of looking at this is an example that is very often used in the way that quantum computing is explained popularly, and that is that if I were to ask you to look at a system, and the system is 0 and 1, and literally how many different ways could you organize those zeros and ones? So there's two inputs, a 0 and a 1. You could have a 0 and a 0. You could have a 0 and a 1. You could have a 1 and a 0. And if you add all of those states up, you get 8 different potential ways in which the 0 and the 1, the input of two states, could be exemplified at any given time. Whereas in a classical machine, it is only ever a 0 or a 1, or a 1 or a 0. It cannot, at the same time, express and handle what we call the superposition of all those states. In nature and in quantum mechanics, the great mystery, we don't know why, and if I knew why, I would win a Nobel Prize. There's a great debate at the moment, or not for a moment, for the last 100 years, ever since quantum mechanics appeared, there's been a debate about why it is. But quantum mechanics is perhaps the most experimentally proven of all theorems, and over again, for the last century or more, we have seen proven the fact that a superposition exists, and that a quantum computer would use that benefit of quantum mechanics and be able to be in many states at the same time rather than simply one. Now, we use the word parallel, or I use the word parallel, to differentiate that from classical computers. And when we're looking at sorting for prime numbers, or the factors of prime numbers, many different ways of encryption today in the world that you and I live in are benefiting from and using the fact that existing computers find it very difficult to get prime factors, and so we can encrypt our messages using such methodology. In the time of a quantum computer, that will not be the case, because a quantum computer will be able to decipher, analyze, and then find the prime factors much more easily, because it can sift through in what we call parallel the many different potential solutions, rather than going one from the other to the other to the other.
So would a really simple example be, let's say I need to clean up my backyard, and, I have to do it normally, pick up all the garbage. But if I had 500 people helping me all at once, the whole thing would be cleaned up quick, because I'm working in parallel with all these people. Is that kind of a real simple idea of how a quantum computer could work in this instance?
Yes, and it's actually a very good example, and it's one that's been used many times, not necessarily your backyard, but sorting, sifting, picking up. There comes a point when that analogy runs out, not because it's a bad analogy, but because actually it's a very good analogy. Imagine if your yard only accommodates a dozen people. So even if you had 500 people, it wouldn't make it necessarily better. So there are some tasks that quantum computers will not be able to do better, as far as we can tell, than classical computers, and there are other tasks that it will. So in the task of prime numbers, using your analogy, your yard will benefit from many more people being in there, because they won't crowd each other out and step on each other's toes, and there'll still be enough yard to pick things up. There are other problems where if you shove 500 people, it'll make it worse and you'll never get it sorted.
So, okay, interesting. So in the area of prime number factoring, which I guess underlies a lot of cryptography, is there enough room for a quantum computer to solve that in seconds?
Oh, yes, yes, yes. I think that there's now very little debate about the fact that cryptography is one of those areas where quantum technologies and quantum computing will have a very big impact. And I think, in fact, governments, well, I would say for the past 2 years, governments and government agencies, both in the United States and in Europe, and almost certainly in China and Russia and other parts of the world, have become concerned about the circumstance in which people that are not sympathetic to their way of looking at the world might have a quantum computer or a quantum technology, which in turn could then be an effective tool for disrupting or intercepting and reading messages which are sensitive. And the most recent adoption of this, shall we say, the space race that has happened in quantum computing has in very large part been stimulated over the last 2 years by the growing realization that what was once seen as a theoretical risk is now a real risk. So the Chinese government, the American government, certainly the UK government have decided to prioritize research and development in quantum computing, largely driven by a concern about cryptography.
So what kind of problems could quantum computing help solve quickly, and which ones can't it solve, or it won't be of any extra help?
Well, 2 quick answers to that, Richard. First of all, like any emerging technology that has such a huge impact on the way that we do things, I suspect that there are a very, very large number of problems that we don't even know will be solved once quantum computers are available and smart people get to work on them. So that's always my big caveat. And I use by way of example the smartphone. When I'm old enough to remember life prior to the mobile phone and the smartphone, and even 15 or 20 years ago when people were talking about smartphones, nobody would have, well, very few people I think would have had the imagination to see beyond the initial communication plus text communication, whereas today my iPhone or my smartphone, whichever brand I have, performs many things and will continue to evolve. So similarly, I would make that caveat, and I really would treat with suspicion anybody who is saying either that they know about all the problems or negatively saying, oh, no, quantum computers will only be limited to cryptography. But you did ask me my own personal view. So with that caveat, which is that I'm a believer in the fact that quantum computing will have an absolutely amazing, revolutionary impact on our lives and the lives of our children, and certainly the impact, in my opinion, will be as great, if not greater, than the last industrial revolution. And my view, I think, is becoming more prevalent now amongst people who are thinking about this. There are 3 or 4 areas in which quantum computing will have a major significant impact. First of all, a very large percentage of supercomputing used today is in looking at new material design. That will be revolutionized by quantum computing. And new materials are essential in engineering, aerospace, for example, pharmaceuticals, for example. This idea that we might one day be able to look at pharmaceuticals and medicines that are specific to you, Richard, or me, Ilyas, rather than the world at large. These are things that become much more accessible with quantum computing. Secondly, I would say anything that is looking at a sort of a probabilistic outcome, and which is at the moment perhaps less than precise. There are very large numbers of industries which rely on Monte Carlo simulation. For example, hydrocarbon extraction, oil and gas drillers, people like that, even pharmaceutical companies. And obviously a quantum computer will have a big impact there. And what's becoming very clear now is big data, the third area. So this idea that data can be used for us and by us rather than we become dazzled by it. this is equally an area which will have a will be impacted by quantum computing. And then cryptography.
Okay. Yeah, a quick tech question. When we talked about the backyard problem that I made up, and you said, there may not be enough space in the backyard for more than, let's say, 10 or 12 people, what is that called? What kind of a problem is that called? What is that space or lack of space called?
Well, at its broadest level, of course, I think computationally, in terms of computational complexity, there's this ongoing debate about P versus MP type problems, polynomial versus non-deterministic polynomial time sort of problems. There are also, maybe extending your point, there are traveling salesman problems, there's knapsack problems. These are, for example, types of problems that existing computers find very, very hard or take a lot of time. And so I think the intuition that people have, computer scientists in particular, I think, have, rather than physicists, is that a quantum computer will make more easy the task of solving certain of these problems. And my own view more recently is that, in fact, that boundary will become extended far more than has traditionally been the thought process, at least for the last decade. Was that your question?
Yeah, I just, what I was asking is, what's the technical name for the space in which a problem exists? And, remember, in the backyard, only 10 people could fit. But if you're trying to find the prime factors of a gigantic number, the space is very different. And that's like a sweet spot where quantum computing seems to shine. So I just didn't know if there's a name for that. I guess the problem space or whatever you'd call it.
No, I'm not. Sorry, maybe I'm missing your question. I don't think there's any particular name. There is, in computer science, a categorization that is measured by complexity. And the easiest way in which people relate to these questions are P, NP, and then within NP there are NP hard, NP complete problems. And so the question of prime factorization is one of those which is seen as, for the sake of argument, if you want to give the label, NP hard. So that is a label that is given to that particular problem.
That works. All right, very good. So maybe it's an ignorant question, but why is quantum computing, why has it been talked about for a long time, and why isn't it here yet? What's so difficult about it?
Well, it is here, and maybe, if I may, would slightly alter why has it taken so long to get to this stage that we're now talking about quantum computing as a reality, and how long will it take before it is a part of our everyday life? And the answer to that question, the first part of the question, is that, again, going back to the late 70s and the early 80s when the terminology first came into being, and as far as I'm aware, and as far as most people are aware, I think that Richard Feynman and David Deutsch are the people that are credited with having come up with the terminology and the thought process that defines and reflects quantum computing. The short answer is that engineering advances were way beyond us. For the same reason that the high-energy particle physics labs, the Large Hadron Collider, for example, the way in which billions or hundreds of millions, if not billions of dollars have been spent on facilities which allow us to investigate the fundamental nature of matter, the engineering advances that have come from there are the engineering advances that have allowed us today in 2016, 2017, to tackle the core issue in building a quantum computer. And that core issue is identifying, manipulating, and measuring in a reliable manner subatomic particles. So photons or electrons are incredibly infinitesimal. A single photon is a single unit of light, And for the vast majority of us, for myself included, even imagining what that means is very, very difficult. And so the engineering tools that we have now available simply did not exist. And in fact, some of the things that we do today, even 25 years ago, many people would have imagined would have been science fiction. So we today have those tools. Engineering has advanced, and that is a simple answer to the question.
Okay, maybe going a little bit deeper. You know, in today's transistors, I mean, we have transistor gate thicknesses of nanometers, and it seems like we're able to manipulate individual electrons, or at least flows of them. How much harder and how much more detailed and how much more difficult is constructing a quantum computer versus, you know, a high-tech circuit?
It's a step change, Richard. It's a complete step change. Well, first of all, actually, the reason, the point you've made is a really powerful one. And over the course of the last 5 years in particular, nanotechnologies, or the ability to have machine tools that can either generate or capture and measure at that level, so that your cell phone, I can't remember now, but it probably, your smartphone has maybe 5 billion or more, 6 billion or more transistors in it. And the single gate fidelity might be 5,000 times thinner than your hair, is a very valid point. But then, from going from that gate fidelity to the manipulation and management of a single electron or photon is an order of magnitude that is measured in thousands. So we're not, it's not comparable. It's the same difference if we're going from small to big. If you're going from a beach ball or a basketball, I think in America basketball is a better analogy than a beach ball, to the Earth. You know, we're talking about thousands of times of magnitude difference.
Oh, wow. Huh.
An electron or a single photon is unimaginably small. You know, 10 to the, if you have 19 zeros before you get to the first one, so 10 to the minus, let's say, 19 meters is the sort of magnitude that we're talking about.
Wow. Yeah, this is a funny question. So what is the supposed dimensions of an electron? Is it like an angstrom wide, or is it
no, it's many dimensions smaller than that. We're talking well, so I guess
wow.
Just turning to physics, and the human mind, interestingly, is much more geared to thinking about and accepting big dimensions. So you and I can talk about the universe, and we can talk about the fact that there might be billions of sun-like stars in our galaxy, and then we can talk about the fact that there may be billions of galaxies, and you know, the human mind kind of somehow understands that and accepts it. Not in detail, but at least that's the way we're geared up. When we turn it the other way and we start talking about infinitesimal, we suddenly lose grasp. And no matter how many zeros we put on it, we kind of quickly lose grasp. So if I said to you that the difference between an atom and an apple is the same as the difference between an apple and the solar system, we kind of lose grasp on that. We just don't really know what that means.
Wow.
So we are talking about, but however, let's be positive. The reason that I think I'm on your podcast and you're talking to me is that we, human beings, humankind, university labs, have conquered those dimensions. Today, it is routine to be able to generate single photons. And that's actually been around for a while. The machinery, you know, for example, a laser-like instrument that could generate a single photon that can then be measured or at least tracked is not something that's at the cutting edge. What is at the cutting edge And the reason why we now have this, shall we say, the new boundary when people like IBM, Microsoft, Google, and others have announced that they're building a quantum computer, not thinking about building, not attempting to build, but either have built or are in the process of building, is that we can now begin to scale from single electrons or single photons to groups. And the challenge now is the decoherence time. And these, again, are very, very, very small amounts of time. But I don't want to get too technical, but that challenge is now being solved. And in fact, this year, meaning 2017, Google have publicly announced, if anybody who's listening is a stockholder of Google, you might get fairly excited, but Google has said that their machine, the quantum computer that they have built, will establish quantum supremacy during 2017.
Wow. So are we going to start seeing the first testing and use of quantum computers, do you think, this year?
Oh, I think that was last year. That was already done. Today, you can go to the IBM website, and they have a 5-qubit machine that is available on the cloud for people to manipulate and use as a test case. And it's not a very sophisticated test, and there is a large debate about how much the IBM people have released, i.e. is the 5-qubit machine that they've released the limits of what they've already built. But even if one disregards that, then these prototype systems are already out there. There are at least, I'm going to say, 5, if not more, university labs that have built small-scale quantum machines from Australia all the way through to the United States. And then there is Google, who I believe have a much bigger machine. And again, this is all in the public domain. I'm not saying anything which is secretive. And if you look at Microsoft, they have made some pretty big announcements about what they're up to. So I think we're way beyond that phase. We're now in an engineering phase. And the question is, at what point will you and I start benefiting from quantum computers?
Quick definition, what is a qubit?
A qubit is the terminology qubit basically is a measure of how many computational steps a computer possesses, and therefore how large or small it is. In a classical sense, we talk about bits and bytes, a 8-bit and a byte, etc., etc. So the equivalent of a bit, a single unit of information, is a qubit. And this is where we started this conversation about comparing, and I used the language of parallelism, but a single bit compared to a single qubit is the element of comparison when we describe size. A 5-qubit computer, the 5-qubit machine, for example, that IBM have, is built from 5 individual subatomic particles. Actually, I'm on IBM. I'm not sure. It might be even after. I don't know the fundamentals of the machine. But a qubit is a measure of size. And just to give you an indication of what that might mean, it is commonly now accepted that a 300-qubit machine would be more powerful than all the computational power in the world currently available put together. So if we could magically plug together every single computer that exists, and we had a power source that could power it, and we put that on one side, and we put 300-qubit, a 300-qubit quantum computer on the other, then in terms of computational data manipulation, the quantum computer would be more powerful, i.e. it could do more things more quickly.
Well, if you're saying IBM may have a 5-qubit computer, I mean, would it be that difficult to make a 300-qubit computer in the near future?
Well, I don't think we should say may have. It does have. There's no question it has. It's on their website, and I know of a number of people, including people in my organization, who have played around with it in order to test certain quantum information theoretic approaches. So, for example, programming. We were talking earlier about factorization, but how do you actually get a quantum machine to do that? You need to write a program, and different people have got different ways of manipulating gates. Your question is how, so that the scaling is the issue. So if you go back to ENIAC in the late 40s, it took from 1948, 49 to get from this room full of vacuum tubes to the point where you have the Apollo space programs and you had computers that were advanced enough and big enough to be able to do something useful in a manner that was measurable. You then went from the late 60s to the, should we say the late 70s, early 80s, before you had PCs. So I'm a big Apple fan, so all of us remember Apple. And that was, let's say, a journey of 14 or 15 years. And then from the early 80s, you get until, let's say, I would say the very early to mid 90s before you start to get the laptops. And then, of course, all of us remember what's happened since. So that journey, where are we in an equivalent time? I would say that it is fair to say that using that chronology, the existing quantum devices that seem to be in prototype use only with a few handful of large corporations and governments today, Google being one of them, Microsoft perhaps being another, IBM being another, the Chinese, shall we say, government being another, and these are just guesses. Those would be somewhere after ENIAC and before the Apollo space mission usage of computers. How long will it take for the equivalent to happen? Certainly there's nobody that I'm aware of that is talking about the same 20 or 30 years. The outliers today would say that we're a decade away from quantum computing being absolutely prevalent in all aspects of our life. And there are some people who think that, let's say in 2 years' time, 2 years is just a convenience, that the number of people that will benefit from quantum computing will be measured in thousands if you define people as governments and organizations. And there is a further line of thought that is very conservative. And for example, if an organization like Google, in its efforts to become the leader in artificial intelligence, starts to use a quantum computer as part of the services that you and I are benefiting when we become Google customers, well then of course you'll measure them in millions, if not hundreds of millions, and there's an argument that suggests that that will happen over the course of the next 2 years. So you have this range of opinion, and I've been along in this business this sector for a while, and I remember distinctly in early 2014 having a debate with one of the great computer scientists and investors around at Cambridge, who was saying that quantum computers will not have a meaningful impact during our lifetime. So in less than 3 years, that embedded opinion has shifted, and my own personal view is that this year, 2017, will see another significant shift so that we will be talking about using quantum computers in a relatively short period of time, measured in less than 2 years.
It's crazy.
Now, there's a company in Canada, not as an advert, but there's a company in Canada called D-Wave who would claim that today they've already reached that threshold. Now, there's a big debate that I don't want to get involved in as to whether that is a true claim or a false claim, but it is a claim that is a legitimate claim that can be investigated.
So what excites you about quantum computing? What scares you? And personally, what do you guess will happen in the next few years, and what problems will be solved, and which ones do you think will still be intractable?
Well, that's such a huge question, Richard. Wow, okay. You don't deal with the small stuff, right? You really want to hit the big stuff. This is good. On a personal basis, on a purely personal basis, it's become very, very clear that we are sleepwalking as a society into a whole new paradigm. And, we in the past have got excited about artificial intelligence, we've gotten excited about machine learning and deep learning, we've got excited about, shall we say, biometrics, and all of that is going to be enabled by this enormous computational power that will start to exist in a period which is extremely, which is much quicker than we've imagined. So let's be conservative, and let's talk about 3 years. Now, when you're a car maker, or when you're a government, and you guys have a new president coming along, 3 years is not a long time. If you're a teenager or if you're my oldest son who's only 11, 3 years is a lifetime. But overall, 3 years is not a lot. So within 3 years, the things that excite me the most are really two things above and beyond everything else. Number one, I think that there will be a paradigm shift in our understanding of computational complexity. And I think that this opens the door for us to look at vast areas which up until now have eluded the power of computers as far as solving. We talked about salesman problem, we talked about knapsack problem, we talked about cryptography, a whole area that has up until now been very difficult for us to become efficient in will open up. And I think that is what excites me the most. And then within that, if I were to focus on one subset, I would talk about quantum machine learning, i.e. a quantum computer enhancing our ability to have an artificial intelligence that allows us as human beings to do things which are beneficial in our everyday lives. I'm talking about drug discovery, I'm talking about new material designs, I'm talking about energy efficiency, even, who knows, even perhaps uncovering the deepest mystery that humankind has always talked about, which, for example, is the ultimate unifying theory for matter. How do we get to quantum gravity? So things like that will be enabled by the emergence of the early quantum computers.
Wow. So stay alive because things are about to become amazing, you're saying, huh?
Yes, I am. And I don't think there's any question that that has now happened. There's an issue of timing, of course, but...
Yeah, it just seems like the exponential nature of this is another area that human minds can't comprehend because things are happening so fast.
I think that the NSA are ahead of the curve. To be honest with you, I think that the white paper I think was issued in October 2015. The dates might elude me, but the NSA website, and they've been talking about quantum technologies and the impact on everyday life. For example, the transmission of money. So if I send you money, or let's forget you and me, let's talk about the Fed sending money, I don't know, to JP Morgan. The NSA have already, a year and a half ago, said that we need new protocols that are quantum resistant. There's no point simply making what we already have better. Now, they didn't specifically say that blockchain might be worrying for them, or SWIFT or PayPal is worrying. They didn't, they didn't specify a particular sector, but they said anything that is not quantum resistant is in danger of being compromised. And a lot of people took that very seriously and have been working at ways in which we can become quantum resistant. So I think actually governments are ahead of the curve on this.
How could you make something quantum resistant? What kind of elements would it need to have in order to be so?
Simple. It becomes a quantum device. So the only way to be quantum resistant, you've got to be quantum basically. So one of the attributes of quantum mechanics is that it is foolproof in the sense of being tamper-proof. So I could send you a signal using a digital device. For example, I could send you an SMS, a text message, and the alternative would be that if you had and I had some sort of a quantum device, I could send you a message that was sent through entangled qubits, let's say, an entangled state. And that would therefore, if somebody tried to snoop on it from the point of view of time when I sent it to when you received it, then A, they wouldn't know what I've sent, and B, you and I would know that it's been tampered with. But these devices are around. There are many companies that, I don't want to scare you, but this is in the public domain. The Chinese have satellites that are based on quantum key distributed technologies, and they've achieved measures of security that are thousands of miles of integrity, and they're way ahead of the curve. If you're inspired after this, go and Google China satellite quantum, and your first 100 hits will be articles about what they've been doing just in the last 2 years.
Wow. All right. I guess from here, I'd just ask, what resources would you recommend for listeners that want to learn more about this? It's fascinating. It's scary. It's amazing.
Do you mean from an academic standpoint or from a commercial standpoint?
Both. Well, first commercial and then academic, but accessible academic, where they could have a chance.
I would say that there are 3 commercial resources that I would strongly recommend if you want a quick dive into what's current. I would first of all strongly recommend spending a little bit of time on the Microsoft website that they refer to as Station Q. It's extremely helpful, very easy to understand, and I would say that would be one. I would secondly do the equivalent at IBM. In fact, the IBM guys have a very neat little video YouTube, which is maybe 3 minutes or 4 minutes, that attempts to answer the question, what is a quantum computer? The third one, these are in no particular order, that I think is really interesting, is a series of lectures by a guy called Michael Nielsen that are pretty accessible, and none of the lectures is more than 15 minutes long. In the lives that we lead, that's pretty accessible. In terms of a book written in a very, very easy to understand manner, there's a guy called Scott Aronson who's at the University of Texas, and he's written a book called Quantum Computing from Democritus. Scott Aronson, Aaronson, and that, I guess, would be my go-to initial book if I wanted to recommend something to somebody who had a bit more time.
Yeah, that's great.
Scott,
some great resources.
And Scott, by the way, Scott, who's a friend of mine, also has a blog. So if you search for Scott Aronson, you'll get to his blog. And you were asking me earlier about ways in which which kinds of problems could be solved and which couldn't. Scott on his website, on his blog, has a whole section devoted to computational complexity, where he explains why even a quantum computer will not. There are certain problems that will not be resolved by a quantum computer.
Okay, great. Yeah, this is it's a completely amazing field and new technology that's coming up, and I could ask you a lot more questions, but you've given me a lot of time, and I really appreciate it.
Great. Okay, well, I hope it's helpful.
You have been listening to Almost Here, Around the Corner Future Technology podcast with Richard Jacobs. Subscribe to this podcast, post a review to discover more future technologies that are poised to transform our lives for better or worse, such as Bitcoin, artificial intelligence, 3D printing, blockchain, virtual reality, and more.
I.e. a quantum computer enhancing our ability to have an artificial intelligence that allows us as human beings to do things which are beneficial in our everyday lives. I'm talking about drug discovery, I'm talking about new material designs, I'm talking about energy efficiency, even, who knows, even perhaps uncovering the deepest mystery that humankind has always talked about, which, for example, is the ultimate unifying theory for matter. How do we get to quantum gravity? So things like that will be enabled by the emergence of the early quantum computers.
Wow. So stay alive, because things are about to become amazing, you're saying, huh?
Yes, I am. Yes, I am. And I don't think there's any question that has now happened. There's an issue of timing, of course, but
yeah, it just seems like the exponential nature of this is another area that human minds can't comprehend, because things are happening so fast.
I think that the NSA are ahead of the curve. To be honest with you, I think that the white paper, I think, was issued in October 2015. The dates might elude me, but the NSA website, and they've been talking about quantum technologies and the impact on everyday life. For example, the transmission of money. So if I send you money, or let's forget you and me, let's talk about the Fed sending money, I don't know, to JP Morgan. The NSA have already, a year and a half ago, said that we need new protocols that are quantum resistant. There's no point simply making what we already have better. Now, they didn't specifically say that blockchain might be worrying for them, or SWIFT or PayPal is worrying. They didn't, they didn't specify a particular sector, but they said anything that is not quantum resistant is in danger of being compromised. And a lot of people took that very seriously and have been working at ways in which we can become quantum resistant. So I think actually governments are ahead of the curve on this.
How could you make something quantum resistant? What kind of elements would it need to have in order to be so?
Simple. It becomes a quantum device. So the only way to be quantum resistant, you've got to be quantum, basically. So one of the attributes of quantum mechanics is that it is foolproof in the sense of being tamper-proof. So I could send you a signal using a digital device. For example, I could send you an SMS, a text message, and the alternative would be that if you had and I had some sort of a quantum device, I could send you a message that was sent through entangled qubits, let's say, an entangled state. And that would therefore, if somebody tried to snoop on it from the point of view of time when I sent it to when you received it, then A, they wouldn't know what I've sent, and B, you and I would know that it's been tampered with. But these devices are around. There are many companies that, I don't want to scare you, but this is in the public domain. The Chinese have satellites that are based on quantum key distributed technologies, and they've achieved measures of security that are thousands of miles of integrity, and they're way ahead of the curve. If you're inspired after this, go and Google China satellite quantum, and your first 100 hits will be articles about what they've been doing just in the last 2 years.
Wow. All right. I guess from here, I'd just ask, what resources would you recommend for listeners that want to learn more about this? It's fascinating. It's scary. It's amazing.
Do you mean from an academic standpoint or from a commercial standpoint?
Both. Well, first commercial and then academic, but accessible academic, where they could have a chance.
I would say that there are 3 commercial resources that I would strongly recommend if you want a quick dive into what's current. I would first of all strongly recommend spending a little bit of time on the Microsoft website that they refer to as Station Q. It's extremely helpful, very easy to understand, and I would say that would be one. I would secondly do the equivalent at IBM. In fact, the IBM guys have a very neat little video YouTube, which is maybe 3 minutes or 4 minutes, that attempts to answer the question, what is a quantum computer? And the third one, these are in no particular order, that I think is really interesting, is a series of lectures by a guy called Michael Nielsen that are pretty accessible, and none of the lectures is more than 15 minutes long. In the lives that we lead, that's pretty accessible. In terms of a book written in a very, very easy to understand manner, there's a guy called Scott Aronson, who's at the University of Texas, and he's written a book called Quantum Computing from Democritus. Scott Aronson, Aaronson, and that, I guess, would be my go-to initial book if I wanted to recommend something to somebody who had a bit more time.
Yeah, that's great.
Scott,
those are some great resources.
And Scott, by the way, Scott, who's a friend of mine, also has a blog. So if you search for Scott Aronson, you'll get to his blog. And you were asking me earlier about ways in which which kinds of problems could be solved and which couldn't. Scott on his website, on his blog, has a whole section devoted to computational complexity, where he explains why even a quantum computer will not. There are certain problems that will not be resolved by a quantum computer.
Okay, great. Yeah, this is a completely amazing field and new technology that's coming up, and I could ask you a lot more questions, but you've given me a lot of time, and I really appreciate it.
Great. Okay, I hope it's helpful.
You have been listening to Almost Here, Around the Corner Future Technology podcast with Richard Jacobs. Subscribe to this podcast, post a review to discover more future technologies that are poised to transform our lives for better or worse, such as Bitcoin, artificial intelligence, 3D printing, blockchain, virtual reality, and more.
If you search for Scott Aronson, you'll get to his blog. And you were asking me earlier about ways in which which kinds of problems could be solved and which couldn't. Scott on his website, on his blog, has a whole section devoted to computational complexity, where he explains why even a quantum computer will not. There are certain problems that will not be resolved by a quantum computer.
Okay, great. Yeah, this is a completely amazing field and new technology that's coming up, and I could ask you a lot more questions, but you've given me a lot of time, and I really appreciate it.
Great. Okay, well, I hope it's helpful.
You have been listening to Almost Here, Around the Corner of Future Technology podcast with Richard Jacobs. Subscribe to this podcast, post a review to discover more future technologies that are poised to transform our lives for better or worse, such as Bitcoin, artificial intelligence, 3D printing, blockchain, virtual reality, and more. Lives for better or worse, such as Bitcoin, artificial intelligence, 3D printing, blockchain, virtual reality, and more.